In this episode of Proof Without Words series, let's look at this proof of how we can trisect any angle in infinitely many steps using only a straight edge and compass. A compass has a sharp leg which you anchor onto the paper and another leg holding a pencil for you to trace out an arc on the paper, while a straight edge is just a ruler without markings. The diagram looks simple enough. We have an angle, and after that, several lines are drawn labeled 1, 2, 3, and 4, with another dotted line. Underneath the diagram, we saw the equation 1/3 equals 1/2 minus 1/4 plus 1/8 minus 1/16. Before we look at the proof, we need to clarify a few concepts. First of all, we can't trisect any angle using only finitely many steps. This problem of trisection of an angle, posed by the ancient Greeks, together with another two problems of doubling the cube and squaring the circle, have long been theorized to be impossible, but a proof wasn't found until the development of an area of math called Galois theory. While it is impossible to trisect any angle using only finitely many steps, the proof above shows that if we allow the number of steps taken to tend to infinity, then theoretically, we will get a trisection to an arbitrary degree of precision, just not an exact trisection. Secondly, while trisection of any angle is not possible, a bisection is always possible. Given any angle, we can always divide it into two equal parts by using a straight edge and a compass. We will see that the proof of infinite trisection angle above is just a series of bisections added up or subtracted from one another. In the diagram, the imaginary line is what we would get if we are allowed to carry on the operations infinitely many times. Now, let's imagine that we start off from the entire angle, and we would like to get to the angle bounded between this line over here and the dotted line after infinitely many operations. For the first step, we bisect our original angle. To do so, we draw a line and label it as 1. So we threw away 1/2 of our initial angle and are left with 1/2 of the entire angle, which is the first term down here in the equation. We then continue bisecting the current angle we have, and to do so, we draw in the line labeled as 2. If we throw away 1/2 of this current angle, which happens to be 1/4 of the original angle, then it seems that we will get an angle which is less than a trisection. To compensate for that, we need to add back a certain portion of the angle. To do this, we bisect the angle bounded between lines labeled 1 and 2, and label the line of bisection as 3. Then add back 1/2 of this portion, which is equivalent to the angle bounded between lines 2 and lines 3. The angle equals 1/8 of our original angle, and after this addition, the current angle we now have lies above the imaginary trisection line again. So now we need to subtract a portion of the angle to get rid of this over addition. To do this, we bisect the angle bounded between lines 2 and 3, we label the line of bisection as 4, and subtract half a portion of this angle, which happen to be the angle bounded between lines 3 and 4, and equals 1/16 of our original angle. So now our current angle is lesser than the trisection we want. You can probably imagine what comes next. We will bisect the angle bounded between lines 3 and 4 to add back half of the portion of the angle so that our current angle is slightly above that required for a trisection again. Rinsing and repeat, that is a general pattern we can spot. For each step of the algorithm, if n is odd, we bisect the angle between lines denoted as n and n plus 1, label the line of bisection as n plus 2, then add back the portion of the angle bounded between line n plus 1 and n plus 2. If n is even, all the steps above are still valid, but at the last step, instead of adding, we subtract the portion of the angle bounded between lines n plus 1 and n plus 2. Doing so, we see that the expression for our current angle equals 1/2 minus 1/4 plus 1/8 minus 1/16 and so on. And the nth term of this infinite sum would be minus 1 power n plus 1 multiplied by 1 over 2 power n. We can use the formula for a sum of a geometric progression to evaluate this, and this gives 1/3. So we know that repeating the algorithm above infinitely many times, we will get as close as a trisection as we want. In fact, after the n step, we will be between 1 over 2 power n away from a perfect trisection. Alright, we have come to the end of the video, and I look forward to seeing you in the next one. Until then.